Good morning, class. As promised, I said I'd go through some of the solutions to the questions I asked you to do for homework last night. So first of all, I'm just going to talk through Boyle's law and the experiment we did in class yesterday. So you need to be able to define it, first of all, that for a fixed mass of gas at a constant temperature, your volume is inversely proportional to the pressure. And when we put this into a formula, we have pressure proportional to 1 over the volume. So when that volume is in the denominator of the fraction, that means, that it's inversely proportional. So when we did our experiment yesterday, we changed the pressure by half a bar each time, and 1 bar is the equivalent of 10 to the power 5 for atmospheric pressure. And we saw as we increased the pressure each time that the volume of the gas in the apparatus was decreasing. So if you were doing this in terms of a graph then, and this experiment will be on your test on Thursday, you have to calculate 1 over the volume. So you'd be taking 1 over 4 centimetres cubed there, and you get a value of 0.25, for example, for 1 over the volume. And then you'd be graphing on your y-axis your pressure in pascals and 1 over volume in centimetres to the power of -3. And you're looking for a straight line graph through the origin, proving Boyle's law. So you could be asked, what does it prove and how? So it shows the relationship that pressure is inversely proportional to the volume because it is a straight line graph through the origin. So that means as the pressure increases, the volume decreases, and vice versa. So you need to be familiar with that graph and be able to explain it. And in an exam question, if you're given pressure as a set of data, you're given volume as a set of data, you'll have to do the work to work out 1 over the volume and then subsequently plot the graph. One of the values being pressure and the other value being 1 over the volume. Alright, I'm going to leave that one with you. Then yesterday we introduced gravity, and we introduced Newton's universal law of gravitation. So using a formula to complete calculations and bringing in this new value which we called the gravitational constant. So Newton's law of universal gravitation is what we call a inverse square law, and it's a big long definition here. So any 2-point masses in the universe attract each other with a force, the force of attraction, and that force is directly proportional to the product of their masses. So product mathematically means multiplying one mass by the other of the first body and the second body, and then inversely proportional to the square of the distance between them. So that would be, in terms of planets, it would be from the centre of one planet to the other would be the distance. That would have to be in meters, and we would square that value. Looking at this in terms of a diagram, if we had 2 bodies, mass 1 and mass 2, we see there the forces acting inwards towards each other, so force of attraction, attracting each other, and we have a distance between the 2 bodies. So the law tells us that force is directly proportional to the product of the masses, so directly proportional to m1 by m2. It is also inversely proportional to the square of the distance between the 2 bodies, so that means F proportional to 1 over the distance squared. So inversely proportional means that distance squared is in the denominator of your fraction. And then when we tie those 2 concepts together, we would have the force is proportional to the product of the masses over the distance squared. And mathematically in physics, if we want to change that proportional sign to an equal sign, we have to bring in a constant. So in this case, the constant we bring in is a capital G, and that is what we call our universal gravitation constant. It's a very small value. It is 6.7 by 10 to the minus 11, and if it's not given to you in a question, you have to be familiar to go to your logs on page 46 and pick it out of your constants table there. So at the end of class yesterday, we tried question 1 very briefly, and I left questions 3 and 5 with you practicing just using that formula. I'm just going to talk through them for a couple of minutes and then we look at our exam question. So question 1 there at the top of the questions, they gave us values for the gravitational constant. They gave us the value for gravity, 9.8 meters per second squared. They gave us the radius of the Earth, the mass of the Earth, the mass of the moon, and the radius of the moon. So you needed various parts of these in some of the questions. So question 1 was straightforward enough. You had to find the gravitational attraction between 2 steel spheres. They were each of a mass of 1 kilogram, and the distance between their centres was also 1 metre. So just filling in your values there, your gravitational constant by 1 kilogram for the first mass, 1 kilogram for the second mass, and your distance 1 metre squared gives you 1. So your force there in newtons actually equals your gravitational constant value, 6.7 by 10 to the minus 11. Then question 3 and 5, you had different values using the same formula. So question 3 asked you to find the gravitational force of attraction between a sphere of mass 90 kilograms and another sphere of mass 1000 kilograms when the distance between the centres was 2 meters. So using the same formula there again and filling in your 90 kilograms and your 1000 kilograms for M1 and M2 and your distance there between them, your 2 squared. So you should have been able to work your way through that mathematically to get a value of 1.508 by 10 to the minus 6 newtons, being the force of attraction between the 2 bodies. Question 5 then, typical exam type question where they will give you 2 different planets or 2 different celestial bodies. So in this case, finding the gravitational attraction between the Earth and the Moon, and it tells you the distance from the centre of the Earth to the centre of the Moon was 3.8 by 10 to the 8 meters. So this is why at the start of the question they were giving us the mass of the Earth, the mass of the Moon, and different bodies there. So we had to fill in our formula again, filling in for M1 the mass of your Earth, filling in for M2 the mass of the Moon, and then the distance between the centres, between the centre of the Earth and the Moon there, squared. And working through the maths, 1.95 by 10 to the 20 newtons was the force. Okay, so that was just an introduction to the gravitational force and Newton's gravitational law. We'll practice some more of them next week again in different concepts. I gave you an exam question then to look at, and this was kind of half of a long question that came up in 2006. So the start of it, you had a few bits of theory to feed back. So define your pressure, state whether it's a vector or a scalar quantity, and justify your answer. Again, a bit of theory, stating Boyle's law, and then you had 10 marks for a calculation in the second half of it, so where you had a bubble of gas in a lake. So this is relating to pressure and volume changing with depth in a liquid. So it tells us that a small bubble of gas rises from the bottom of a lake and the volume of the bubble increases threefold when it reaches the surface of the lake. They give us atmospheric pressure acting on the surface of the lake, and they tell us the temperature is 4 degrees Celsius. So 2 things they're looking for us to work out for the calculations here. What is the pressure at the bottom of the lake, and what is the depth of the lake? So a bit of work here to do in the calculations. They gave us acceleration due to gravity, g, being 9.8 meters per second squared, and they gave us the density of water, being 1 by 10 to the 3 kilograms per meter cubed. I gave you a few hints here for the calculation part, First of all, what does increases threefold means? So threefold means multiplying by 3 or times 3 the volume increase from the bottom to the top. So we can physically see there in the diagram as well, the bubble is increasing to 3 times the size of its volume. So if the volume is increasing 3 times from the bottom to the top, then we need to think about what's the pressure change in the opposite direction from the top to the bottom. We know from our pressure in a liquid that pressure increases with depth. So that pressure will increase 3 times for that bubble from the top to the bottom. So our total pressure at the bottom will be times 3, an increase of the pressure at the top of the lake. There's a trick to the second part then. I gave you another hint there. The pressure at the bottom due to the water is the total pressure minus atmospheric pressure acting on the surface. So we'll look at that in a second when we look at our marking scheme. Marking scheme here, the first part we had 3 bits of theory, 6 marks each going for them. You had to define pressure, so you can define it using words. Pressure is force per unit area. If you write down the formula, capital P is equal to F over A. You see there in the marking scheme it says to explain notation. So if you write down capital P is equal to F over A, besides that you have to write P equals pressure, F equals force, and A equals area. So defining what each of those variables are is explaining your notation. So either way, using words or using the formula and explaining each of the terms will give you your 6 marks. Second part was asking if pressure was a vector quantity or a scalar quantity and to justify your answer. So it's a scalar quantity because pressure acts in all directions. It doesn't have one specific direction. So if you think of submerging a piece of wood into liquid, there will be forces acting on all sides, above, below, and to the sides of it from the liquid. So it is a scalar quantity acting in all directions. Again, theory there, state Boyle's law. So pressure is inversely proportional to volume, and you have to state for a fixed mass of gas at a constant temperature. So people very often have the first 3 marks there and they forget to add in the second half of the definition for a fixed mass of gas at a constant temperature. And if you're writing it in terms of a formula and you write P proportional to 1 over V, again you have to explain your notation there. P standing for pressure and V standing for volume. The calculations then. So it tells us that the volume of the bubble increased 3-fold. So that means its volume increased 3 times from the bottom to the top. So then the pressure will have decreased 3-fold, going from the bottom to the top. So if we're calculating the pressure at the bottom of the lake, we have to remember that the pressure increases with depth, and because they gave us the atmospheric pressure of 1.01 by 10 to the 5 pascals acting on the surface of the lake, it must be 3 times this at the bottom. So 3 multiplied by your 1.01 by 10 to the 5, the atmospheric pressure, gives you the pressure at the bottom of the lake, 3.03 by 10 to the 5 pascals. Part 2 is asking for the depth of the lake. So we must use our formula for pressure in a liquid. So pressure in a liquid is depth or height by density by gravity. And there's a trick here where the pressure at the bottom due to the water is the overall pressure of the 3.03 by 10 to the 5 pascals minus the atmospheric pressure above it. So just due to the water there is 3.03 by 10 to the 5 minus 1.01 by 10 to the 5. So the pressure due to just the water at the bottom is 2.02 by 10 to the 5 pascals. You then would write down your formula for pressure in liquid, pressure being height by density by gravity, and rearrange that to get the height or the depth on its own. So the height or the depth will be the pressure divided by the density times gravity. So the pressure is just the pressure due to the water itself, not the atmosphere above it. And this catches people in this type of question. So 2.02 by 10 to the 5 divided by the density of the water times gravity. So the depth there of the lake we can work out in meters, 20.6 meters. And you see there, if you leave out your unit, -1 mark for leaving out your meters for your depth. So always include units in your answers. Alright folks, I'm going to leave that with you. You are doing a bit of study for the rest of the class today, and you're studying this evening. Your test tomorrow is chapter 9 and 10, and it's very similar format to your Christmas test. There will be 3 experiment questions, pick 2 out of the 3 to answer, and there will be 3 long questions, pick 2 out of the 3 to answer. Same format as Christmas for the long questions as well. The first one will be the 12 small parts, pick 8 out of 12, and then the other 2 are full long questions there. Alright, so best of luck, and I'll see you next week again. Bye.